Hi everyone. In today's session, we are going to talk about a deep learning network from scratch. So basically, we are trying to code a network from scratch. We will not be using any built-in functions. We are trying to use all the formulas which are available on internet and trying to compute the gradients and the error matrices. So let's see how the network look like in the next slide. So this is the network architecture we are using. We are having two features, X1 and X2 in the beginning. We are having a hidden layer containing two nodes. We are having the output layer containing two outputs. This is a binary classification use case. So we are using softmax activation in the final layer. And in the hidden layer, we are using ReLU. In the last, you can see we are trying to compute the errors, E1 and E2, and total E, which is computed based on the value of Y1 hat and Y2 hat, which are the predicted values that are coming out of the network. Just to remind you, a binary classification use case can be done in two ways when it comes to the last layer of the network. We can have one single node in the last layer and use a sigmoid activation, or we can also use two different nodes in the last layer for a binary classification along with the softmax activation. So let's go to the details, a few of which we've already discussed. So it's a binary classification use case. We talked about the network layers and number of nodes. The total number of weights that we're using is 8, W1, W2, W3 till W8. ReLU and softmax are the activations. And the training consists of total 100 samples. So that means you have 100 data points and we have a batch size of 10. That means these 100 data points are going to get converted into a batch of 10. That means we are going to have 10 iterations over the entire data set at once, right? And then we are going to have 300 as the value of total number of epochs. So one epoch is the one total iteration that is done for the complete data set. That means one epoch will include 10 different batches. One batch has 10 samples. So 10 batches would include all the 100 samples, which is the entire data set. So that means one epoch has these many samples or batches, right? So we are going to have 300 epochs like this. Now, this is just an example to explain you the code. Now, the optimizer that we are using is Adam. So on the right-hand side, you can see how the training process looks like. It's just a high-level view, right? So batch one starts in the training. So in the initial stage, we are randomly initializing the weight values. Then sample one goes into the network, which is step B. That means you're trying to do forward propagation and the backward propagation for the first data point. When you do the forward propagation for first data point, let's say we get the values of y1 predicted and y2 predicted as shown here, 0.9 and 0.7. Now, when we apply softmax activation, the values of y1 hat and y2 hat are converted to 0.8 and 0.2. The function of softmax activation is to convert the value of two outputs in the binary classification in such a way that their sum becomes 1. As you can see here, 0.9 plus 0.7 was greater than 1. So we converted these two values in such a way that the total 0.8 plus 0.2 is equal to 1. Then we compute the error, which is the log loss error. Then we go to the back propagation. We compute the gradients of the errors with respect to all the weights used in the network. Then these two steps, forward propagation and backward propagation, is done for sample 2, sample 3 till sample number 10. And once we are done with sample number 10, that concludes one batch. Now through each of the samples, sample 1 and sample 2 and so on, we would have got some gradient values. For sample 1, we would have got a gradient vector containing the gradient values of errors with respect to W1 till W8, and so on for all the samples. This can be explained using a basic write-up. So let's say you have 8 different weights, right? So for sample 1, gradient vector would look like this. Let's say and so and so. So there will be total 8 different terms in this. This is just random data. Now the same thing will be computed for sample 2, and it is going to have some different data. But again, total data points in this vector is going to be the same 8, because there are 8 total weights. So the error gradients also would be 8 for these 8 weights respectively. The same process is continued for all the samples till sample number 10. Let's say this also has some sort of a gradient vector. I'm just modifying the values quickly to show you a different vector, right? What happens now is that you compute the average value of gradient vector for entire batch. Just to give you an example, this will be a 8 numbers vector. So there will be 8 values in this vector. The value 1 will be computed by taking an average of 0.12, 0.23, 0.93. So these are total 8 values. We divided by 8. So what we are doing, we are taking the gradient of W, the gradient with respect to W1 for sample 1, the gradient with respect to W1 for sample 2, the gradient with respect to W1 for sample 10. We take all of them, we take a mean, and that gives us a value of 0.7. So this becomes the first value in the average gradient vector for the entire batch. Same way, we will have 8 different values over here. So this is how you compute an average gradient vector for the entire batch. That's what is written here. Calculate average of all the gradients with respect to the weights. Now, what do we do next? We use this gradient vector, which is this one, which is computed for the entire batch. We use this in our gradient descent algorithm to update the weights. How it is computed? So in the initial stage, when the network started training, we had given a random weights to all the network branches, right? So weight vector in the beginning was, let's say, so there will be 8 different numbers here, and your gradient is this after the end of first batch of data. So your weight vector updated would be weight vector old minus learning rate into the average gradient vector, right? So basically you are trying to update the weights by using the gradients which you have calculated in one complete batch, right? So that is about how do you update the weights using gradient descent algorithm by doing forward propagation and backward propagation for one complete batch. That's the same thing which is written here. The error gradients is used to update the values of weights using an optimization algorithm, which could be gradient descent as well. Now, the same process which we explained starting from point number A till E, this is carried out for all the batches of data. So we have 10 batches. We just now concluded for batch 1. We will conclude for 2, 3, 4 till batch number 10. And then we would have covered all the data, all the 100 samples that we have. Then we will do the same process for the other epochs as well. The weight at the end of the last epoch would be the final weights. Now, the next thing is looking at the code, which would require a bit more technical details. So let's go ahead with it. So the code starts as follows. You basically have the input data and the expected data declared in the beginning itself. So you have an input data frame containing 2 features, x1 and x2, and your expected output is 0, 1. Right, so it's a binary classification use case. So your y1 hat is 0, your y2 hat is 1, right? So now what we do exactly in case of back propagation and forward propagation when it comes to the network. Three parameters that you notice in the beginning. One is the batch size. So I've kept a batch size as 10. So number of samples in a batch is 10. And the total number of samples I have taken as 20. So that means batch size is 10. That means there will be 2 batches per epoch. And I have taken 4 epochs for this use case. A learning rate is taken as 0.35. And the algorithm that we are going to use here is mini batch gradient descent. So there are other variations of gradient descent. One is a batch gradient descent and another one is stochastic gradient descent. We're using the third one, which is mini batch gradient descent, which includes basically treating the batches of data while doing the weight updates. So let's see the code now. So we start from here. We are passing the input data and the expected output data to the network. This is what we're doing here. So just to give you a reference, your input data would look like this. It will be a data frame. I'm not able to represent a data frame in a notepad, so let me just write down quick values. So you'll have x1 and x2. So let's say x1, x2, right? Then you'll have x1 and x2 for sample 2, and so on. So you have 10 samples. That means you would have 10 different lists inside the outer list. This is just to represent that there will be 10 different samples and each sample would contain 2 different features, right? Now your weight vector, initial weight vector, would look something like this, which is randomly initialized. That is what we're talking about here. And the weight vector is a variable that we use for loading the subsequent weights. Right? Then comes the basic for loop, wherein we are doing the epochs and batches and samples. Just to reiterate how this works in so that it is clear. The first thing is an epoch. The second thing is a batch. Third thing is a sample. One epoch is a one round of entire data set. Data set, let's say, contains 20 points. Now, one epoch means you should be able to iterate to all these 20 points at least once. Your batch here is of 10 samples. That means you would have 2 batches in a epoch. Then you have samples or data points, which is 20 points, which is already listed above. Now, since you have these 3 different levels of loop, that's why you see 3 for loops: the outer for loop, the inner for loop, and the last for loop. The first for loop is for the epoch. Second for loop is for the batch. Third for loop is for the sample. So the process remains same, what I explained. Let's see how the batch starts. So when you start the batch, you pick an input data ranging from number 1 till number 10. Because for a batch, you have 10 samples, right? So here I'm picking all the 10 samples at once. Then I'm initializing a default gradient vector value. So it will just have blank values as of now, and just initializing a random or a default error vector. You can ignore these 2 as of now. There's nothing much happening here. The main thing is you have an input data containing 10 samples for the batch number 1. Then you go through the innermost for loop, which contains all the 10 samples. So what we are doing here, we are basically computing the gradients and the errors by passing the input data sample or the input sample and the weights vector to a function, which is forward propagation, backward propagation function. So basically for every sample, you're trying to compute the error and the gradient, because you already know from the computations that we did before that for every sample, we are going to compute the gradient, which we are doing in the innermost loop. When we come to the outer loop of the batch, that means when we have already computed the gradients for all the samples in the batch, we do an average. That is the same thing that you see here, gradient vector dot mean. Once all the samples are finished for the batch, then we do the average of the gradient vector. Then we also discussed about the weight update using the gradient descent algorithm. That is what is happening here. Update weights using the gradient descent algorithm. This is the gradient descent algorithm basic formula. So weights old minus learning rate into the gradients. And then you're calculating the errors. So errors also, what happens is you compute one error for one batch, right? So you would compute one error value for every sample. That means for one batch, you would have 10 different error values. At the end of a batch, you would compute a mean or an average to compute one single error value for one complete batch of 10 samples. That is what you compute here. Now, before going further, let me give you an idea of the graph. So this is the batch numbers which are shown on the bottom side, 0, 1, 2, 3, 4 till 7. So we had 8 batches in our example here. Now the error for the batch 0 was this much, and the error for batch 1 is this much, and the error value for subsequent batches keeps on decreasing. This is when I ran this algorithm. And this is the error value in form of an array to understand better. So with every corresponding batch, the error value keeps on decreasing. Now let's look at the other key things here. There are other few functions which you should look at. One is the binary cross entropy error, then the sigmoid activation and the softmax activation, and the forward propagation, backward propagation. Let's see the forward propagation, backward propagation. So what we do here, we basically are trying to compute the Z values and the A activation values. And then in the end, we are trying to compute the error using binary cross entropy error. All the equations that you see here, I have actually derived those equations and have uploaded the derivation process online on SlideShare. I will pass on the link to you. You can just look at it as well. So this is the reference network. These are the equations for forward propagation. This is the error related equation. And then you have gradient computation related equations. So whatever output I got from these equations, I have just fed the same data to this function, right? Now, this is here where we are computing the gradients. And as an output of this function, we pass the gradient vector along with the error. The other two functions, which are sigmoid, so we have implemented them using the formula. So formula is very straightforward, 1 divided by 1 plus exponential minus z. And the formula has also been implemented for log loss error as well as the softmax. So this brings us to the end of this code. I would recommend you please go through the code. I will give all the details in the description and you can let me know in case you face any issues. Thank you so much, everyone. Have a great day. Bye-bye.